Morning everyone. So today we're going to start into our last chapter in Chem 12. This is going to be Unit 5 in Electrochemistry. So we can just start a fresh new page here. As that name suggests here, we're interested in this chapter in studying sort of the interplay between electricity and chemistry. At first we're going to study essentially how a battery works. We're going to use chemical reactions, so that's the chemistry part. Use reactions to produce electricity, so getting some useful electrical energy out of the system. And then towards the end of this chapter, although we're going to be working with exactly the same data booklet table and everything, we're actually going to find that some reactions that are non-spontaneous, that just don't happen, we can actually force to happen using electricity. So that's sort of the converse here. Use electricity to run a chemical reaction. Right? But essentially, it's that interplay between how does electricity relate to chemistry back and forth. The main type of equation that we're going to be looking at is going to be referred to as a redox reaction. Redox reaction is actually split into two parts. We'll start off with this ending part here with the ox. This ox here actually stands for an oxidation reaction. For the longest time, oxidation had been defined many different ways. It's rooted in that word here, oxygen. So many of these reactions do involve gaining oxygens. But eventually they had discovered what oxidation reactions actually have in common is actually in oxidation, we actually have a chemical, a species, actually loses electrons. So for example, let's take sodium. Sodium is a metal, okay? It's a solid, it's an alkali metal. Upon losing electrons, right, you can imagine sodium is on sort of the third row, it has 3 shells. Imagine taking the outermost electron, the least held electron, removing that electron. I haven't touched the core, so we are still sodium. But previously we were sodium as an atom, we were neutral. Having lost an electron, now I'm going to have the free electron loose in nature, and now I'm going to actually have created the Na plus ion. So we're going to see an oxidation reaction has electrons on the right hand side, and we say the sodium as the reactant, this is the chemical that was oxidized. This is the one that actually lost electrons. Turns out an oxidation reaction cannot happen by itself because we're going to be just delivering off all these free electrons. Charges in general are unstable. So unless someone is willing to pick up these electrons to sort of attract these electrons here, the oxidation reaction won't happen by itself. So the other side of this equation here is this reduction part. That's this first part. For a reduction reaction, you guessed it, this one here is a species. It actually gains electrons, and I'm just writing electrons as E minus. So for example, if I have a fluorine atom, fluorine has 7 valence electrons. If someone is willing to give it its electron, that electron can be added to fill up that last spot, and then now we have a full noble gas configuration here. So we have a fluorine grabbing an electron, ending up becoming fluoride. Electrons on the left hand side actually means a reduction, and it's always the reactant that we talk about here. The reactant is a thing that has been reduced, okay, as opposed to reducted. Throughout this chapter here, there's a lot of little memory aids for yourself. So we'll come to the first one here. We'll start off with Leo the lion says grr, and we're just going to write grr, G-E-R. Okay, and that's how you sort of shorthand. Well, loss of electrons is oxidation, while if you have a gain of electrons, so we're talking about changing charges, gain of electrons is reduction. Your workbook also likes using like oil rig, so if you like that one instead, you can say oxidation is loss, while a reduction is gain. Now, even as you start thinking about the terminology here, usually when we think something is reduced, we usually think about, oh, something's coming down, we're losing stuff. It's a little bit strange to define a reduction as a gain. It just turns out the things that we're collecting and gaining are actually negatives. What's actually being reduced, what's actually coming down is actually our charge. We may actually be a positive charge, and then as I get more negative things here, my charge ends up dropping. Or I might be neutral already to begin with, and then as I pick up electrons, it's going to keep making my charge even lower. So let's just start off with a reaction that we've seen before here. Let's start off with a piece of iron nail. We're going to drop into solution of copper sulfate. We did this one here last year. Basically, your copper sulfate is in solution. Copper sulfate is actually a bluish color. What we had done is we dropped in an iron nail. We left sort of half of it unexposed, half of it exposed to the copper sulfate. What we found over time was we ended up getting a coating of another material because it looked like something has happened in solution that actually tells you a chemical change has occurred. So if you look at sort of trying to balance this equation, styling what type of equation this is, this one should be a single replacement. We have a metal that's by itself. Because I sort of watch it happen, I would assume that the iron here is actually more active. Being the more active metal, it's going to be able to kick off the copper no problem. Iron is going to be multivalent, so technically it could be iron 2 sulfate or iron 3 sulfate here. Usually if I know the charge, sulfate here is actually a -2 charge. Copper is using as +2. I'm going to pretend just use iron as a +2 then with sulfate. Remember at this point here we're just guessing anyways. Poor old copper who got kicked off is now copper solid, and that actually deposit on the nail, even as speckles in the solution, that's actually just pure copper metal. This single replacement reaction here can now be reframed as a redox reaction. If I just sort of dive through the detail, what's happened to the iron? Iron went from being the Fe, this is the neutral form, this is the atomic form, in becoming FeSO4, this is the iron in the 2+ form. Which side would I have to add electrons so that the charges would balance? Well, iron here has a neutral charge. Iron +2 is now higher by 2 charges. What I need to do is I need to add to the side that's higher, and I need to add 2 electrons. So in this case here, the reactant that's involved in this process, the electrons on the right-hand side, as iron becomes Fe2+, it loses these 2 electrons. We say the iron here has been oxidized. Right? Again, if no one is willing to pick up those electrons, this can happen. Very similar to our acid-base chapter. If someone is willing to give up protons, someone else better be willing to gain those protons, or else the transfer won't occur. The copper one is a little bit harder because it's sort of not written out just as a ion. This copper sulfate actually involves copper 2+, and then eventually we're going to end up with copper 2+ becoming just copper metal. Well, what's happened to it? For me to bring my charge down, I need to undergo a reduction reaction. There's 2 positive, so I need to gain 2 negatives. And in that case there, we still remain copper. If electrons are on the right-hand side, it's a reduction. The chemical that was involved is now referred to as the chemical that has been reduced. Okay? So just let me write that down again here. We do call it together a redox reaction. A redox reaction involves transferring electrons. Unlike the acid-base chapter, obviously we're passing electrons, not protons, but in the acid-base chapter we were just dealing with 1 proton transfers. In this case here we already see, well, every time this first reaction occurs, we drop 2 electrons. Fortunately, the copper +2 wants to also pick up those 2 electrons. That way I have no free electrons in nature. So redox reactions involve transferring any number of electrons from the species oxidized, the species that upon losing electrons, to another species that is reduced. Okay. So let me just give you another example of this. Just first types of questions are just identify who got oxidized, who got reduced, and then we'll introduce another term with this question. So I'm going to give you this equation. It's already balanced for you. 2 aluminum, 3 copper +2. This one here, one-way arrow becomes 2 aluminum +3, and then 3 Cu. Whenever they're asking you to identify, so let's do this as part A. Part A, I just want you to identify who gets oxidized and who gets reduced. We are always talking about identifying the reactants. After the electrons have been transferred, we just happen to create these 2 other guys. Some of these reactions are reversible, so you could also say, well, who then gains and loses to go back the other way? But based on the way it's written, it's a one-way arrow. I want to pick between aluminum and copper +2, who's oxidized and who's reduced. You can think through the definitions. You can say, Leo the lion, well, oxidation is a loss of electrons. If I lose electrons, my charge should actually increase. Well, here we go from aluminum, and then we suddenly go to Al +3, you'll notice my charge has actually gone up by 3. Because this charge has gone up, I would predict the reactant that was involved, this is the chemical that was oxidized. How about reduced? Again, generally we think of reduction as a loss, but we're actually going to define, no, reduction is actually gain. We're actually gaining negative things. And what's actually coming down is actually my charge. If I go from copper having a +2, I'm going to ignore the coefficients for now. Going from copper in the +2 state to copper, this one here ends up becoming just +2, so it's dropped by 2. I would have had to gain negative things for my charge to have come down like that. Again, it's the reactant that was involved, therefore the copper +2 is the thing that gained electrons. Okay? So always referring just to the reactant side. Let me introduce to you one other definition here. So similarly, I just want you to identify, so between the two reactants again, can you identify something referred to as the oxidizing agent? I'll give you the definition for that. An oxidizing agent is a species, it's a chemical that helps another oxidize. It helps something else lose electrons. Usually, this is just a nice memory aid for us, but itself usually gets reduced. So if I ask for a definition, I want you to see that first part. Well, as an agent, I'm supposed to help someone oxidize. I'm not the one that's actually oxidizing. Imagine you went to the store and you bought a cleaning agent. The cleaning agent, the detergent, whatever you buy here, that thing isn't the thing that needs cleaning. But that thing helps you to clean other surfaces. So in this case here, we had identified, well, aluminum was a chemical that needs to be oxidized. This is the one that needs to lose electrons. This is the one that the charge needs to go up. What chemical is actually allowing the aluminum to lose electrons? Again, were it not for copper +2, were it not for the other ingredient, aluminum would just sit around not doing anything. So in words you can describe here, because copper +2 is in solution, copper +2 is actually the oxidizing agent. Copper +2 allows the aluminum to oxidize to Al+3. Right? If this one weren't there, aluminum wouldn't actually oxidize. Notice the copper +2 is actually the one that we labeled. This is the thing that actually gets reduced. So copper +2 is the oxidizing agent. It allows aluminum to oxidize. And in a similar fashion here, if I ask you, can you identify or label the reducing agent? Again, as an agent, just remember, you're not the chemical that's, in this case, you're doing the reduction. This is the species that helps another reduce. It helps something else gain electrons, and typically, right, but itself gets oxidized. Right? That's not always true, but in general, in this case, we have copper. This is the thing that's going to reduce. It's because aluminum was in solution that was willing to actually give it electrons. Copper's +2 is just waiting around for these electrons. Oh, perfect. Because aluminum is there, that's the reducing agent. Aluminum gives electrons. So copper +2 can reduce to copper. Okay, and I just want to point out to you here, whenever we're labeling who gets oxidized, who gets reduced, who are your agents, I am just always looking at reactants. After the electrons have been passed, we just happen to end up forming those products there. In this question here, it was a little bit simplistic because we just have pure elements and then we have charges. I can see very clearly when charges go up and when charges go down. Sometimes, though, the chemicals themselves are a little bit harder. We saw a little gist of it earlier. Sometimes we have copper sulfate. Well, unless I really thought about, well, what charge is copper using, it's not immediately obvious. Copper is actually going from 2 to the elemental state. So what we're going to do here is we're actually going to create up a new system. This system here is going to be assigning something called oxidation numbers or oxidation states. We're going to make up some numbers so that if this number goes up, we know it's oxidized. If this number goes down, we know it's actually reduced. There's actually no chemistry in these rules here, but I just sort of simplifies things a little bit here so we can track and label who's oxidized and who's reduced. So the section here is dealing with oxidation number or oxidation state. For the longest time, so oxidation number is usually like a digit. Like my oxidation number may be +1, while oxidation state is usually a Roman numeral. Well, maybe I have a 1 to be +1. Nowadays, they just use these terms just interchangeably here. But basically, I'm making up a charge so that if the number goes up, oxidized. If the number goes down, I know I've gained electrons. I know I've been reduced. How this system works here is when you assign oxidation numbers, what we're doing is we're actually assign a charge, assuming the chemical we're looking at, assuming the chemical is ionic. Okay, so let me just give you a quick feel of this. If the compound is ionic, it's not too hard. If I ask you for sodium chloride here, well, what charge is sodium using? You'd say this is +1. Well, I'm going to pretend it's ionic. What charge is sodium? Well, this is now referred to sodium as oxidation state is actually +1. How about chlorine? What is its charge? Its charge here is actually a -1, right? So I'm just going to give it a name. That's actually the oxidation number as well. Strangely enough, when you actually assign these oxidation numbers have to always be the sign first, then the number after. Okay, so they're super picky for whatever reason. If you put 1 minus, it's actually wrong. You actually need to put the sign first, -1. So usually I just tell people always do the sign first. 90% of the time it really doesn't matter. In the case that it does matter, like in oxidation state, you'll have it correct. Now, we're not seeing the sort of the significance of this oxidation number, oxidation state yet. But what if we start looking at, let's say, sodium chlorite? Okay, so I balanced off the charges there. Realistically, this compound actually contains 2 types of bonds. The sodium here is plus, the ClO2 is going to be minus. There is an ionic bond between the metal and the non-metal portion. But we see that the non-metal portion is not just an element. The non-metal portion is actually a polyatomic compound made out of non-metal. That part there is actually covalent. That's realistically what's happening there. That's actually somehow sharing electrons. What we're going to do for oxidation numbers, we're going to say, let's ignore the fact that's covalent. Let's pretend this entire thing is ionic. So I have this compound, I have NaCl and O2. If I were to just sort of piece by piece, just ask you, well, what charge is the sodium? What charge is the chlorine? What charge is the oxygen? That's assigning the oxidation number, pretending the whole thing is ionic. And as I walk through your rules here, essentially you're going to say, well, sodium is usually +1. Oxygen here, if it were charged, it would be -2. Realistically, in the covalent compound, it's not charged. But if I just pretend for a second, well, O usually gets a -2. We're going to get a rule later on that I had worked out these charges that overall we actually had no charge overall. So whatever chlorine has to have in this compound, I can write this out in terms of the math here. Sodium plus whatever chlorine should have plus 2 times whatever oxygen has have to give you an overall charge of 0. What would the charge of chlorine be? You can either work that out in terms of the algebra here. 1 minus 4 is going to be -3. Chlorine minus 3 has to be 0. So chlorine is like having an oxidation state of +3. Is that a real charge? Has it really lost 3 electrons? No. But this is a number that I can assign to it. This compound here realistically does not have this +3. But if chlorine on one side is kind of like a +3, on the other side maybe it's 0. Oh, when 3 goes to 0, it's been reduced. This is just an easy way for you to track whether it's oxidized or reduced. So what we're going to do here is I'm going to introduce a bunch of rules. How do we start assigning these oxidation numbers? You will get a lot of practice with this one here that you just memorize these rules here. Not too hard to remember. First one, anything that is in its elemental state. Anything that's sort of in the way that it typically appears in the neutral atomic state, we're just going to assign it as 0. So let's take a metal here, let's say silver. If I say, what is the oxidation state? Someone hands you a block of silver. Although silver usually takes on a +1 as a charge when it bonds, this is just silver as an atom. Atoms by nature are neutral. We're just going to say this silver here is 0. Or we can have copper. Copper, right? Metal, right? Again, it could be +1 or +2 when it bonds, but right now here it hasn't bonded yet. Copper here is just going to be 0. We just assign it a charge of 0. Let's do a diatomic like fluorine. Fluorine here is actually going to be an F and an F. What we're going to find for this oxidation number, the oxidation number, these rules here is always defined. Oxidation number is defined per atom, per each atom. So earlier we were saying loosely oxygen is actually -2. Well, I happen to have 2 of them. Each oxygen with -2 totals is -4. So here we have fluorine, it's F2. I want to tell you, well, what's the charge on fluorine? What's the charge on fluorine here? Again, this is the way that it normally appears. This is a diatomic compound, so be it. This one here, it's the way it naturally appears. It's a neutral molecule. I'm going to say this is 0, this is 0. Sometimes you do run into compounds, especially when you have similar elements here. Sometimes one could have been +1, the other one could have been -1, but we're just going to keep things really simple here. If it's in its elemental form, if it's in the normal way it appears, we're going to assign each of them as actually 0, so therefore the F2 also has a 0. We're going sort of from easy to hard here. Second part here, equally easy. If I have a very simple ion, I'm going to assign it an oxidation number of its charge. So earlier I was saying silver, as a metal, it's 0. What if silver becomes a positive charge? That is its only charge that it has. Well, if I pretend this is ionic, well, this is an ion. Let's assign it. Sign first and the number, +1. Let's go F minus. So fluoride, right? If I pretend that this is negative, well, this one here, the fluorine by itself was actually a 0 oxidation number, but when it starts bonding here, when it's gained an electron, it actually takes on -1. It has an oxidation state of -1. So if it's simple ion, it's just that one element. I already have the charge in the corner. I'm just going to give you that charge there. Okay. Third rule here, your oxidation number or oxidation state, again, those terms can be used interchangeably. Oxidation states add to give the overall charge. Now, usually in an ionic compound, we work out the ratio of the positives and the negatives until the charge is canceled anyways. Sometimes the compound, the grouping is actually charged. Let's just do an example of this here. Let's do H3PO4, phosphoric acid. Again, in a typical ionic compound, we would have worked out the charges that the overall charge is 0. What this rule basically says is, whatever charge hydrogen has is per atom, there's 3 of them, 3 times whatever H has, plus whatever phosphorus has, plus 4 times whatever oxygen has to give you 0. Okay, that's this rule here of oxidation state. Evidently now I'm going to need to introduce, well, some elements will always have certain charges, and then we're just going to do some algebra to solve for the unknown. The ones that we're going to know here, rule 4, rule 5. Rule 4 refers to, well, hydrogen and alkalis are going to appear in a lot of compounds here. Alkalis, so alkali metals, group 1. When these appear in compounds, I'm going to assign an alkali pretty much always a +1. And along that same vein, although hydrogen itself is not quite an alkali metal, hydrogen also usually takes on a +1. You can even throw in there an alkaline earth metal is always +2, but typically this is good enough. So in this case here, we have hydrogen. What if I assume hydrogen here is a +1, right? So each of these hydrogen gives me a 1 charge. There's 3 of them. That gives me a total of +3. There is one other one that we need to note here is oxygen. Oxygen in compounds, it is usually going to be a -2. I'll do an exception with you in a second here. So I need to assign for you, well, if oxygen here is actually a -2 of a charge, I have 4 of them. In total, they're going to add to give -8, although I would say per atom of oxygen it's still -2, what ends up making the math easy. I want you to get enough practice that without actually showing this algebra, you can just do it by inspection. So phosphorus, I don't have any rules for. I'm just going to use rule number 3. Phosphorus takes on whatever charge it has to have to cancel out whatever the 3 hydrogens, the 4 oxygens, and ending up giving you an overall charge of 0. So let me just show you through that math there. Again, I want you to get enough practice that you don't need to show this algebra. 3 times hydrogen as a +1 plus whatever phosphorus has minus off the 8 that comes from the 4 oxygens has to give you 0. So I have 3 plus phosphorus minus 8 has to give 0. 3 minus 8 is -5. So P minus 5 is 0. And therefore P, sign first on the number, P is an oxidation number +5. It's like the phosphorus is in the +5 state. Is that a real charge? Has phosphorus really lost 5 electrons? No. Realistically here, this is a covalent compound. There's actually no charges involved. But just for the purposes of identifying, have we gained electrons or lost electrons here? We just want to assign that charge. Now, those are the standard cases. Now I figured out phosphorus is actually +5. I don't want you to memorize. Okay, now every time I see phosphorus, it's going to be +5. Phosphorus in this compound is actually +5. Okay, what if it happens to be in another compound? So let's give you another compound. Let's take H4 P2O7. Okay, so earlier phosphorus is in the +5 state. Let's see if we can work out this one. Hydrogen here is a +1. There's 4 of them. That gives you a +4. Oxygen is usually -2 times 7 is actually -14. Plus those 4 gives you -10. two phosphoruses here have to add up to end up canceling the overall charge. In this case here, phosphorus just so happened to also be +5. Okay, so sure, there are other compounds that phosphorus actually has +5. There are many other groupings where phosphorus is actually not +5. So for example, if it ends up just becoming neutral phosphorus, phosphorus sometimes comes to us in the state of P4. That's elemental, so that's phosphorus without having bonded to anything. In that state there, the phosphorus here is actually in the 0 state. So I have 4 atoms of phosphorus, but all 4 of them are actually 0. Now, we're going to see 2 other exceptions here. What if I have a metal hydride? What if I have like sodium hydride like that? It's an ionic compound that the hydrogen is actually taking off the charge of a nonmetal. In this situation, we're actually going to have, sodium here is supposed to be +1. Hydrogen here is supposed to be +1. Our problem is going to be when I add up these two charges, I have a total charge of +2, and yet this compound here is actually 0. So what I'm going to do, as I listed these rules here in order, if I find that sort of rule number 3, sodium plus hydrogen is supposed to give you the overall charge, but rule 4, when I do this hydrogen rule here, it ends up disobeying an earlier rule. I'm going to keep the earlier rule, and I'm going to change the later rule. So what I'm saying here is whatever sodium has plus whatever hydrogen has to give 0. I'm going to keep that rule. The alkali will typically take on a +1. If hydrogen, for this instance, wasn't actually +1, what would hydrogen have to be to make sure they actually give 0? In this case here, hydrogen as a nonmetal is actually -1. So in a really rare case, sometimes hydrogen is actually going to be -1. More often than not, it's going to be +1. And I'll give you one other exception here. Let's do H2O2. All right, so it's a peroxide. Again, our rules say hydrogen should be +1, oxygen is usually -2. Again, the charges don't cancel out. 2 times +1 gives you a +2. 2 times -2 gives you -4. 2 minus 4 actually gives you an overall charge of -2. And yet, rule number 3, nope, they have to add up to give 0. Well, which rule came first? The hydrogen rule came first. So let's keep the hydrogen as a +1. Let's temporarily change the oxygen. These are fake charges anyways. But what charge would the oxygen have to be so that 2 of these oxygens, whatever their charge is, have to cancel out the overall charge? We're going to change the oxygen here also to a -1. So every now and then, it's also -1. Sometimes your oxidation state is actually going to be a fractional number. Totally okay, because these are not real charges. I just want to indicate to you whether the charge goes up or the charge goes down. So let me just end off with one question here as we practice through these oxidation numbers. For example, I'm going to give you cyanide reacts with IO3 minus. This becomes I minus and then CNO minus. Okay. Exactly the same question as I asked you earlier. I want you to just identify which species. So identify the species oxidized, identify the species reduced, and since we talked about those agents, identify the oxidizing agent and the reducing agent. Okay. We see that this question here is actually a little bit harder because first thing, we don't have all simple ions. We have like polyatomics here. I do have a simple ion over here, and yet I is sort of in compound. I don't really know what charge I has. Here's where oxidation number actually helps you. One caution before we actually practice through the problem. Whenever you're asking for labeling which species did which, remember we are always only talking about reactants. So even after the electrons are transferred, we just happen to have created I minus and CNO minus. Obviously, the electron transfer can go the opposite way as well. But when you're answering this problem, you should be looking at the chemicals that are actually doing the bonding. What I want you to do for practice here, I want you to assign, step 1, assign oxidation numbers. Assign these fake charges so that I can tell if the charge goes up or goes down. Assign oxidation numbers to everything. And how we're going to be sort of looking at these numbers here is if your oxidation number increases. If it goes from a small number to a big number, we can write that down. The change in oxidation number actually increases, or a change in oxidation number is positive. That's actually going to be an oxidation. Okay. If the oxidation number decreases, if the change in oxidation number, if I go final minus initial, if this one here is actually a negative number, this one here is actually going to be a reduction. Okay. So I do want to get some practice just assigning oxidation numbers. This will actually help us out with balancing later on as well. Just go through and assign absolutely all the charges for everything. Let's start off with really easy ones. I minus is a simple ion. If I pretend that this one here is ionic, which it is, I is sort of like in the -1 state. Let's take a look at this CN compound. Now, unfortunately, I don't have any rules for this, but between these two ones here, who normally has a charge, a carbon or a nitrogen? Nitride is usually going to be a -3. If I give nitrogen the -3, although realistically this is covalent, realistically they aren't really charged -3 like that, what charge does carbon have to have upon minusing the 3 from nitrogen gives you the overall charge of negative? You should be able to tell me here, carbon is sort of like being in the +2 state. Is that a real charge? No. Let's go on here, IL3 minus. The oxygen is usually going to be -2. There's 3 of them that MS in -6. Iodine minus 06 has to give you a -1. Iodide is currently in the +5 state. And then let's do the last one here. Again, the nitrogen is usually -3. The oxygen here is usually -2. And when you get enough practice that, as I'm doing by inspection, you can just go, whatever carbon has, -3, -2 has to give to the overall charge. The overall charge this time is actually negative, so therefore carbon should be in the +4 state. So all I'm doing is I'm assigning these oxidation numbers. The charges weren't very obvious. But now that I have sort of looked through the compound and I actually found the charges, I can say, what happened to carbon? Carbon went from sort of like being a +2, and later on it's become a +4. You'll notice that oxidation number has actually increased by 2. Increase actually means oxidation. The reactant that was involved has been the chemical that was oxidized. Why is that? Well, oxidation, remember, oxidation is actually a loss of electrons. For my charge to actually go up, I would have had to toss away negative things. Perfect. That's your oxidation. How about IL3 minus? IL3 minus, it's actually the iodine part of the compound. The iodine goes from a kind of +5 down to a -1. This one has actually dropped by 6. I would have had to have gained negative things, gained electrons for my charge to come down. The reactant that was involved is therefore the chemical that was reduced. Remember, electrons are passed from where it was lost, where it was oxidized, to where it was reduced. So what I'm saying here is we actually have electrons that originate on the cyano compound, and they're actually passed over to IL3 minus. It doesn't always have to just be one electron, but definitely passes that way. Lastly, we have oxidizing agent, reducing agent. Well, an oxidizing agent helps something oxidize. Well, I know the CN minus oxidizes because IL3 minus is around. The IL3 minus is also the oxidizing agent. While the reducing agent, it helps something get reduced. It is the iodine part of the IL3 minus that gets reduced. That's only because CN minus is present. The reducing agent is actually CN minus. Notice as I'm labeling them, I label the entire compound. I know it's probably just the iodine part and just the carbon part, but all of these refer just to the reactant side. Okay, so just have a look over these terminology here. Make sure you're comfortable assigning these oxidation numbers, and then we'll go from there. Thanks, guys.